industries. He has invested the majority of his career in sales-focused roles, but has extensive hands-on experience in field work, including installations, troubleshooting, and maintenance. Matt is an experienced trainer in all aspects of lubrication used in reciprocating compression across the U.S. and Canada. His current position as senior sales representative for national accounts allows him to bring his vast application knowledge to the industry and affords him opportunities to collaborate on industry's most challenging issues. In addition to being a part of Sloan, Matt is on the board of directors of the Eastern Gas Compression Roundtable, where he has served for 25 years in various capacities, including chairman of several prominent committees. Matt resides in Saxonburg, PA, along with his wife, Colleen, who also works at Sloan as a manufacturing manager. With that, Matt, thank you so much, and please take over.
Thanks, Chuck. Appreciate it. Okay.
Yep.
Great. Well, thanks for having me join your conference today. Again, my name is Matt McCarthy with Sloan Lubrication. We're happy to have an opportunity to be here today and present a little bit of our information on oil and gas compressor lubrication. Primarily, we're talking about the force-fed lubrication, not the crankcase splash lubrication. So we'll focus in on that as we go along. But let me give you a little history of Sloan Lubrication. Started in 1922 by 3 Sloan brothers. Today, we've grown to become a leading manufacturer of lubrication systems, products that we design and build, and we've grown to over 50 employees to support the network of manufacturing, engineering, customer service, installations, and after installation support, including service. So as force-fed lubrication systems have grown and changed over the years, we've begun now to really revolutionize what we're doing. And towards the end of this presentation, I'd like to talk a little bit about what reducing lubrication rates means to the industry today. But primarily, force-fed lubrication supplies on integral engines, such as a Cooper or an Ingersoll Rand, the power cylinder lubrication, as well as the compressor cylinders and rod packing cases. The on separable compressors, such as the aerials and superiors, we provide just lubrication of the compressor cylinders and rod packing cases. So let's first determine how do we calculate what's required, and then talk about the equipment that it takes to get it there. So a compressor cylinder needs to have a continual delivery of oil film on the cylinder walls that lubricate the cylinder as it goes back and forth. This film is continually replaced by the loop system as the oil carries away, as the oil is carried away in the gas stream. Providing too much oil and you'll flood the downstream piping and reduce the quality of the gas. Providing too little lubrication, and there will be accelerated wear on the components. So it's critical that we calculate what's necessary to put into that cylinder, so it's not too much, not too little, and here's how we do it. So compressor cylinder, we do the geometry first. We'll take the diameter, or the diameter of the compressor cylinder, and we're going to multiply that by the stroke length of the travel. We're going to multiply that by the RPM of the compressor piston, and then that result is then divided by a constant, which is provided by the industry standards. Typically, over the years, it's been a pint in 2 million square feet when there's been iron on iron in a cylinder, and just standard oils. A pint in 2 million square feet is a 32,000 divider, which goes right into that constant below. Divide that into stroke bore RPM, and you'll get the total required oil delivered requirement for one compressor cylinder. Then if there's 1 or 2 loop points on that cylinder, we'll split that evenly between those 2 cylinder points. Now, over the years, when rider bands and wear materials got better, and some places used better oils, it's more specific to compressor cylinders, we can go to a pint in 3 million square feet. So typically we're going to use that 48,000 as the constant in today's applications. It's also dependent upon the quality of the gas stream. So if you've got good, clean, natural gas quality, quality gas through the transportation, we can use a pint in 3 million square feet every day. If we've got gas coming out of the field and it's a wet gas, a Marcellus gas, and you've got more particulates to deal with in the compressor cylinder, we may still use a pint in 2 million square feet. So, excuse me. All right. If you're on that integral engine, if you're involved with those, then the power cylinder lubrication gets calculated out as well. And that's part of a dual zone system where we're doing compressor lubrication and we're doing power zone lubrication. Power zones are calculated by using the brake horsepower of the engine times 8, which is 8 pints in a gallon, times 24, which is 24 hours in a day. Then we're going to divide that by a constant, which is provided by the manufacturers. For example, in the Cooper-Bessemer GMW series, that number is going to be 7,000. Now, the resultant answer to that is how much oil the engine needs totally, and that will be divided evenly amongst all the power cylinders. And then on each power cylinder, it will be divided evenly amongst the number of feed points on each power cylinder. Now, if you're doing a 4-cycle engine, such as a Ingersoll, KVS, KVRs, there's only valve guide lubrication, and for those we calculate 0.05 pints a day per valve guide. So in our example here, this is a Cooper GMVC. It is an integral natural gas engine. That means, for those who are not familiar with the integral side, that means this is the engine and it's integrated with the compressor cylinders, which come out on the left side here. And then they're banked down along the crankcase. So we're lubricating dual zone in this situation, power zone and compressor zone. And in this specific instance, we have all of our lubrication equipment just lined up on the end of the engine for easy access and visibility. The lubricator box, which is part of the component which drives and force feeds the oil down into the system, is driven typically by the engine. We can also drive it by an electric motor. We can control it in our tri-sip systems. We can have integrated PLC packages that completely run the whole unit off engine. In this particular example, we've got 2 zones, as I said, one for power, one for compressor. So we have a pair of pumps for each zone that are adjusted to the proper flow rates based on our calculated requirements. These pumps individually feed divider blocks. Now, a divider block takes the oil from the pump and splits it into the required distribution points at the proper amounts on a slow frequency of cycling to slowly deliver drops of oil to each lube point over the operating 24-hour period. So it's small quantities of oil over long periods of time to provide that film thickness we're looking for. Each of the divider blocks may feed secondary divider blocks, which are mounted out on the compressor cylinders. So a typical package here is a lube pump with some sort of driving mechanism. We're going to feed that from either a day tank of compressor oil, or we're going to pull it out of the crankcase of the integral engine and use that oil to provide the cylinders and packing cases their lube. So on this particular example, this is a 1,000 horsepower, 300 RPM engine. So each compressor cylinder is 11 inches in diameter, and there's a 14-inch stroke. Applying our stroke times bore times RPM is 11 times 14 times 300. And then from the chart, we know that a GMVC requires, or the pint in 4 million square feet swept area is, a pump, sorry, pint and 3 million square feet swept area gives you 48,000 as the divider. So we're looking at 0.96 pints a day, or about a pint per day per cylinder. Now, if you were calculating out the power zone, we're going to use the 1,000 horsepower times 8 pints in a gallon, 24 times 24 hours in a day. We're going to divide that by the OEM spec 10,000, and we're going to provide to the power zone a total of 19.2 pints per day total. And then we're going to divide that up among the 6 power cylinders evenly. So that's where our calculations come from. How do we get it in there? Well, we're going to force oil through from the loop pump through this divider block mechanism, which meters and delivers the oil in the proper proportions. Now, in the old days, there was a pump for every loop point called pump to point. Today, it's divider block lubrication systems. Now, in the old pump to point, operators would adjust each pump to see a drop of oil in the sight glass drip at a certain fixed frequency. 10 drops every minute would deliver 1 pint a day. So if you needed half a pint a day to feed your packing case, we're going to adjust that pump to 5 drops a minute. Over time, that changes. Pumps wear, maybe it wasn't locked in and the vibration starts to make the pump adjust differently. So a pump can clog up, a pump could go bad. And there was no way of knowing that if a pump wasn't delivering the proper amount, that it was not right. So if an operator went by every day, took a look at the pumps, he had to measure every one of those feed points. And on that example in the Cooper, we're going to have 6 cylinders with 2 loop points on each one. That's 12 pumps. Compressor side, we're going to have 3 cylinders, another 6 pumps, plus the packing cases, another 3. So we've got quite a number of pumps and quite a number of drips to be looking at. Not paying attention to that, you might go days, weeks without all of the pumps delivering the right amount of oil. And eventually you'll start to see a wear because you're under lubricating, or you might see excess oil going into the gas stream because you're over lubricating. So the divider block loop system was invented at that time to give a more automated delivery with the ability to protect the oil delivery by monitoring it with a PLC or some sort of a control mechanism. So let me explain how a divider block works. Internally, there are pistons or little spool valves that move back and forth, forcing oil down each oil line one at a time. And it's forcing a measured fixed amount of oil, depending upon the size of that divider section segment. They come in multiples of 6, 9, 12, 18, 24, and 30. What those numbers mean is 0.006 or 6 thousandths of a cubic inch of oil gets delivered out of a divider segment for every motion of the piston in one direction. 6 thousandths of a cubic inch of oil is about 3 drops. So if you equate that back to the old 10 drops a minute is a pint a day, you're going to know that every 6 motion gives you 3 drops of oil at the end point, at the loop point. Now, oil is fed through from the pump into the divider block, and it is channeled through a back network in the base plate, which feeds one piston at a time. So only one piston moves at a time, and it's a series progressive divider block. So as it moves all the way across and delivers its oil down the first outlet, it opens the spooling to allow the oil to move the second piston, which then opens the spooling to allow the third piston to move. The entire thing reverses, and the first piston moves back to the original point, and second and the third. So when all the pistons move to the right and then all the pistons return to the left, that's called one cycle of divider block. Now, this is going to happen at a fixed frequency based on the adjustment point of your lube pump. So if you're looking for that 8 pints a day to be delivered to the compressor zone, you're going to adjust this pump unit to deliver oil that feeds a cycle frequency that calculates out to be 8 pints a day. So how do we know what that is? We're going to take the total displacement of the block. So if we add up the numbers, 6, 9, 12, whatever those divider segments are, and we total that number, and we multiply it by 2 because the pistons move in both directions, you're going to get a total displacement of the block. So if these were all 6 T's, they're going to add up to 6, 12, 18 times 2 is 036, 0.036 cubic inch displacement per individual cycle of the block. So how do we monitor that? We're going to watch that one piston move back and forth with this cycling indicator. It's a visual indicator. So as the piston moves across, it's going to move this magnetic gold band out. And as the piston returns, the gold band moves back in. So we're visually watching the internal motion of those pistons. So if we took the displacement we calculated and we multiplied by a magic number of 3,000, which is comprised of 86,400 seconds in a day, and we divide that by how many cubic inches there are in a pint, which is 28.875, we're going to come up with the number almost 3,000, 2992.2. So rounded to 3,000. So that is how we calculate displacement times that magic number, and we divide it by the calculated cycle time of that visual indicator. So if I were able to calculate that, set a timer, and I watched the gold band move out and rest while the other 2 pistons move, and then I watch that gold band move back and rest until it starts moving again in the same direction for the second time, that's 1 lap of the timer. So as the band moves out, the first piston's moving, then the second piston moves, then the third piston moves, reverses itself, and the first piston goes back. So that gold band goes back in and rests while the next 2 pistons move. So I cycle time from when it moves to the right, all the way to the back, and then right again. Set a timer when it starts moving for the second time. You're doing a lap 4 or 5 times, get an average, and you can throw that cycle time into our calculation. So that's the manual way to do it. The automatic way of doing it to your PLC is using a proximity switch. Now the proximity switch is an electrical converted device that trips a reed switch with a dry contact, which is then wired into a PLC. And these values of calculation are fed into the PLC to do the automatic calculations. Now, as the gold band moves back and forth, so does the proximity switch, giving us the time frame which we can put in the PLC and set a displayed flow rate based on our calculation so that you can make adjustments just by looking at the computer monitor and adjust the pump setting until the flow rate hits the proper value. Then you lock in your pump. Now the computer can watch, or the monitor, we have a wizard monitor which is displaying the current flow rate. We're going to watch that and set an alarm value point. So if the flow rate intended to be 8 pints a day falls off to an alarm set point of 7 pints a day or 6 pints a day, we're going to have an alarm triggered which will alert operators that there's a problem. So divider blocks were designed to replace pump-to-point lubrication systems which had no protection against lack of lube or low lube with a more automated way of doing it. One pump needs to be adjusted rather than 16 pumps. So that was one of the major inventions in time as lubrication components have changed. Now, in order to know that this system is doing the job that we expect it to be doing, we need to do a lot of testing of the divider blocks on a routine, regular basis and make sure that our pumps are in reliable condition. So in order to know that divider block is working right, we provide this test criteria recommended on an annual basis. The parameters are that if you were to, we take a divider block, which is on the engine, we take it off and put it on a test stand. We connect in our hand pump or a purging pump, and we flow oil through the divider block, seeing visually that oil comes out all the holes. Very nice, slow, gentle flow of the block, simulating the pump that it's connected to when it's on the engine. Now, once we verify that the block can flow free to atmosphere and it takes less than 500 pounds, and in a brand new block, we're seeing 200 or 300 pounds to cycle. So the delivery pressure for the hydraulic fluid going through the block cycles and moves all the pistons at less than 500 pounds. The next step is to cap off one line at a time and force a failure by simulating a plugged line. So then we'll pump up the oil to 3,500 pounds and we let it sit for 2 minutes. And we want to make sure that oil does not bypass and bleed around those internal pistons or those spools and go to other lubrication points. So we want to be sure that that piston fit, which is very critical to forcing oil down the line at high pressures, we want to make sure that that piston fit is good. By pressuring it to over 3,500 pounds, holding it for 2 minutes, we're going to see if that oil is sliding around the pistons and going other places. You're going to see the pressure gauge fall off. We can't tolerate more than 500 pounds of pressure falling off over the 2 minutes. Now that's a brand new block. If it's out in the field and it's been operating for a year or two, the condition is that we test for 1 minute. But a brand new block has to be as good as possible, so we're going to test for 2. When you're doing these tests, we're looking for a couple of key things. Bypassing, which is the oil sliding around the pistons, and bleed down, which is bleed down on the pressure, and then the actual cycle pressure, which is the pressure it takes to cycle the block to atmosphere. So if you give us a call and you're testing blocks and you're having some problems, these are the questions that we need to ask you. And these are the words that will help us understand if you've got a problem with your divider block. So again, we verify, first of all, that the test pump is good and in working order. Remove all the lines from the block, connect the test pump, and run a purge, get the air out of the block. Pump slowly and watch for pressure less than 500 pounds. Block the outlet with a cap, pressure to 3,000 or 3,500 pounds, and time it for a minute. Test each outlet consecutively, one at a time. You can't put caps on all the outlets, pressure it up to 3,000 pounds, wait a minute. That's not the way it's done, although that's a common misconception in the field. So troubleshooting lube systems. From our experience, the first steps often taken in troubleshooting only do more damage. This is due to the fact that very few mechanics have real world experience with these systems. Typically, a lube system is installed and it's in working condition, it's fed oil, and it just runs for years as is without any testing. So when something does go wrong, oftentimes the mechanics don't have any experience with the systems and need to turn somewhere. So make sure that we have a good line of communication with your people, and we can walk you through any troubleshooting. So in that system, there's a protective rupture relief between the pump, which can generate 8,000 pounds pressure, and the divider blocks and the terminal checkpoints. So between the pump and the divider block is a safety relief valve we call a rupture disc. The rupture disc is designed typically on our systems to rupture at about 3,000 pounds. So if a line downstream is plugging up, a check valve is starting to fail, as the pump continues to pump oil downstream, it's going to raise pressure if you can't deliver oil against one injection port. So as the pistons jam up against the downstream blockage, the pressure rises in the system. And before something breaks, like a pump blowing off its mounting, we're going to rupture a relieving valve, like you said, about 3,000 pounds. So that'll safely vent that excess pressure back to atmosphere pressure, and it's fed back into the system. So once that rupture disc is blown, no oil is going to get downstream to any of the divider blocks or any of the lube points. And the divider blocks then stop cycling because there's no oil flowing through them. Once they stop cycling, that proximity switch, which is the electrical interface to the PLC, stops changing state. As the block doesn't cycle, the reed switch doesn't cycle, the PLC will time out against an alarm set point and trigger a compressor shutdown. So what happens at that point? Your compressor shut down on lube fault. You go out and check if the rupture disc's blown. If it is, then it's downstream pressure that's caused the problem. Properly designed lube system includes pin indicators on the front of every divider block. So you start looking for the tattletale signs, pin indicators, which would relieve out a little pin that indicates the line where the excessive pressure comes from. You can use that as a trace mechanism to find which check valve may have failed or which lube port may have plugged up. If there aren't any pins out, perhaps the divider block is locked up with air. So air is detrimental to the operation of the divider block, and it requires purging to get the air out of the system again. So if you let a tank run dry or did some maintenance and didn't properly purge oil throughout the system and you left some air in the lines, eventually that'll become a troubleshooting issue and we'll need to work on purging again. Now, let's say the divider block didn't rupture a disc. There was no excess pressure. Your lube system may have run shy of oil, or a filter could have plugged. So check your oil supply to the pump. Make sure that you've got a good, clean oil supply. Again, running a purge once you check that the oil supply is sufficient. Lube pumps, drive fail. Maybe a coupling has spun apart. Maybe when the engine or the compressor is turning the lubricator box, that coupling has come apart and now it is no longer driving the pump. Or the pump could have had a failure. A Sloan system is built with a spare pump already in the system. So if it's a dual zone compressor and power system, there's a pair of pumps for the compressor side and a pair of pumps for the power side. So each pump can be turned on with this backup spare turned off. So if you're trying to troubleshoot the system, turn that spare pump on and see if you get your flow rate reestablished. Turning off the first pump, and if you've established the flow and it's fixed, you know you have to come back and change that bad pump. Another thing to look for in troubleshooting is an electrical monitoring failure. So is it a wiring issue or is it a hydraulic issue? If you've got no ruptured discs and the pumps seem to be pumping and you see the visual indicator cycling on the divider block, then it's typically going to be some sort of an electronic failure. It's not hydraulic. System's working. We're just electronically not reporting that it's working properly. So there could be a problem with the proximity switch. Could be a loose wire. If it's tied into a PLC, it could be a bad PLC card. So the electricians would come in and take care of any electrical issues. So emergency repairs. Another critical factor is how prepared are you for emergencies. Spare parts are critical in an emergency. Do I have the spare parts necessary? How long can I be down? Do I have time to fix this? Do I have the skills to fix this? Do I have 5 engines in a row and I can afford to take this one out of service? If I've got 2 units running and I've got to have them both running, I need to have the skill level to be able to do the repairs on site. I need to have the spare parts necessary to do the repairs immediately. What can I substitute in a pinch? Can I take a divider section that's a 6T and put it where there's a 9T? All these issues can be discussed. You just give us a call and we'll work you through those. We also will provide training on site so your personnel are ready to go in an emergency. We can work out spare parts lists for you and provide you online technical support, in-person technical support, and we could talk you through it virtually. But to prevent emergencies, the best thing to do is have a regular maintenance plan in place to be able to test divider blocks on an 8,000 or 16,000 hour basis, to be able to replace pumps, repair pumps, test pumps, change divider blocks, change rupture discs. So what we recommend is an annual maintenance program. Filters, we need to change filters, replace the rupture disc every year. Rupture discs see cold starts, and it's one of the least expensive components in the complete loop system, and it's a whole lot better to change that rupture disc once a year than it is to have it fail prematurely. Test those divider blocks according to our testing procedures, and again, you need to make sure that you have good operational testing pumps so that you can provide that maintenance on site. Switch pumps, go from that built-in spare to the operating pump, switch back and forth so that the spare doesn't always sit. We want to operate those pumps on an annual basis. Turn one off, turn the spare back on. Check lube box reservoir and change the oil. Change the gear reducer oil. If you've got an electric motor driven lubricator, we want to change the gear reducer oil there. And if you have a day tank that supplies the oil to the lube system, we want to inspect that day tank and we want to make sure that it's not full of contamination. So lube rate reduction, we've got all these components in place to be able to properly deliver the oil per our calculations. And we know that our systems are in good shape. You always want to make sure that that's the case before you start a lube rate reduction program. So our flow rate constants for those compressor cylinders we talked about before was a pint in 2 million square feet or a pint in 3 million. Today, we've been able to provide the industry with our tri-sip lubrication system, which can actually reduce oil flow rates to a pint in 20 million or even as much as a pint in 30 million square feet. We do that through the special oils that's involved, the tri-sip fluid. And the benefits of reducing your oil savings, exactly the cost of oil delivery, gas quality in the gas stream. We're going to be able to, with a better gas stream quality and less oil going out from over lubrication, we're going to be able to reduce pigging, and we actually increase valve life as well. So the tri-sip package, we're doing a case study where by the end of 2020, we're going to have 134 units installed on a gas system line. The projected savings, this will reduce the oil by about 36,000 gallons of oil usage over the system over a period of a year. Obviously, if you're putting that much oil into the system, you're going to have to pig it. You're going to have plugging regulators in the with the oil in the gas stream. You're going to filter coalescer changes more frequently, and even clogged pipelines. You're running a pipeline that's been collecting oil in the low spots through the mountains. It's just clogging up the pipe and allowing less open volume for oil for the air to flow past this oil. So you have to pick that out. The Tri-Sip Lube package will increase the delivered gas quality to your customer and increase the compressor valve life. So give us a call if you want to talk about how we can further reduce your oil using the Tri-Sip lubrication system. So I hadn't seen any chats. Have you seen any in there, Chuck? Any questions that we can handle?
I am not. Give me a moment. Let me just take a quick look. Let's give our guests a couple of seconds to ponder and see if anything pops up. But as of right now, I don't have any questions on my queue.
Okay.
Thank you, Matt.
I did not see any come in on my side either. So yeah, we'll give people here a couple minutes to ask. So don't be shy and just make sure your phone is unmuted or send a chat over to on the screen there.
Hey, Matt, a long time ago, somebody mentioned to me the lubrication test of the compressor was getting adequate lubrication is take a cigarette paper and hold it up against the cylinder and see how well it stuck. What was that all about?
That's
I've heard that before, I assume.
The cigarette paper test. Of course, how many mechanics carry cigarette papers in their toolbox, right?
Right.
And why does that mechanic have cigarette papers?
That's another question.
It's actually still taught at Ariel in their system training classes. Cigarette paper tests. If you took 2 cigarette papers and put them on your finger and touched them to the cylinder wall, then let them go. If there's too much oil, excess oil on the cylinder wall, the cigarette papers are both going to absorb that oil and they're going to stick. They're going to stay there on the wall. If you have the proper amount of lubrication, you have 1 paper falls, 1 paper stays. Inadequate lubrication, there's not enough fluid on the cylinder walls to let either paper get stuck.
Okay, interesting.
So, it's an age-old question. Does it really work? I think it's exactly how they used to do it back 50, 70 years ago. I mean, you know, it's something we do when we go in and do a study on an aerial. We'll go in and take a look and actually do the cigarette paper test. So we have that in use, and it's based on the aerial recommendations.
Yeah, it's been described to me that a lot of compressor manufacturers probably overestimate the lubrication feed rates, and that's just kind of what your thought was on that, and how much, you know, I got to assume lubrication costs are just phenomenal for the amount of horsepower installed just in the Marcellus, Shale, Utica areas. And you know, are you doing studies that show how much money we can save you can save, excuse me, by doing that? And if you had any case studies where that might have been the case? Yeah.
Towards the end of the presentation, I talked just a little bit about our Tri-Sip lubrication. It's going to dramatically impact and change the industry as we know it as far as lubrication rates go. To be able to reduce, as I showed you, from 36,000 gallons of oil not going into the pipeline, that's dramatic numbers. We can reduce on a typical aerial compressor from their recommended flow rate sheets, which calculate their oil anywhere from a pint in 500,000 to 1 million. And keep in mind, our regular recommended rates today is a pint in 3 million square feet of swept area. And so this excessive lubrication can be reduced by using the tri-sip package. Our fluids, especially fluids, are designed to work very well with the polymers of the Teflon polymers. So we can reduce flow rates to tenths of pints a day from 60 or 80 pints a day to compressor cylinders. And that's talking overall tenths of a pint, half a pint a day to each bank of cylinders. So reducing oil reduces how much oil is going down the gas stream, and that's a big content today.
Sure.
The quality of gas being delivered to the customer is increased dramatically by reducing the oil content.
Thank you. Sorry if my question was redundant. I had to step away for a minute, so I might have missed that. I apologize.
No, that's fine. It's a great thing to reinforce is that we're changing the industry again. Now that it's getting legs with one particular company, we're going to have a lot of quantifiable data based on these 134 units that are going to be in operation by the end of this year.
And you guys will perform the full retrofit based on the equipment that you recommend?
Absolutely. We would go in, we do a study of the individual compressor. We verify all the data. We'll recalculate flow rates, redesign delivery, divider block delivery sizes. We will come in and the tri-sip package actually comes in that unit by itself. I'm going to go back one step here. Are we still displaying my PowerPoint there?
Yes.
Okay. So essentially the tri-sip unit is everything's in the box. There's a electric motor driven lubricator that's controlled by a PLC. It's self-contained HMI, tells you when it's time to change your oil reservoirs, and it automatically maintains the lube pump speed so that the precise amount of oil is being delivered to the cylinders. We'll set that package in place, bring some power to it, tie it into a PLC for shutdown, and it can communicate by a cell back to a dashboard that gets monitored for lubrication failures, and we can track and trend data. But essentially, the heart of the system is the fluid, the tri-sip fluid that we put into the compressor cylinders. It's specially designed to work with the wear materials and extend the life of wear materials and reduce the required oil. So we'll put that package in place, run new tubing, set up the divider blocks, purge everything, get it started and running, and there you have it.
Great. Thank you.
Sure.
Great. Thanks, Matt.
Certainly.
Are there any other final questions for Matt? Okay, well, Matt, thanks again for presenting today. We really appreciate your time to share with us your expertise and about lubrication and how to apply that